processing a message block and associated data block at a time for each compression function call, storing the associated data into the intermediate chaining variable. When we finish with processing the associated data, we continue only with the message, and to ensure that there will be no forgeries, we have to change the domain separation value in the tweaks. And then at the end, we produce the tag using only a message input and a chaining variable, and depending on the situation with the padding, we choose the value for the final J component from this set. Then what could happen is that we have the same number of blocks in associated data as we have in the message, and in that case the processing looks like this, and you see that the set for the values for the final call is now different, because otherwise we could have some easy forgeries. This is how it looks like when we have a bit untypical case, but it's possible still, that the message is shorter than the associated data, so that we just start processing as in the previous two cases, processing a block of message and a block of associated data at a time. And as soon as we run out of the message blocks, what we want to do, we want to finish processing the query as fast as possible. So here we start partitioning the associated data in a different way. We start to partition it into full width blocks, and we have to use different value for domain separation again. And for the final call that produces the authentication tag, the set for separation values is yet different, because now the inputs come only from associated data but not from the message. Then there are a bit special cases. If we have no associated data, the pure OMD scheme looks just as the old OMD. So we have this Merkle-Damgard chain where we only input message blocks and encrypt message blocks, but the red components of the tweaks have different values as with OMD. And this is what it looks like if we have only associated data. Again, we want to make the processing as fast as possible, and it looks like this. And to make the algorithm well defined, we also cover these very rare cases where we either have very short associated data, one single short block, or two empty inputs. So this is a bit strange, but it's something like we want to authenticate that we are saying nothing. And you can see that a very important role in the design is played by the delta masking sequence. It's basically the core of the design which keeps everything secure. And that's why you want to choose very carefully how you compute these delta masking offsets. And there is twofold criteria to this. One criterion is efficiency. You want to make this computation efficient so that the scheme is usable, and security. So you need to make sure that the way you compute these masking offsets will allow you to have a secure scheme. If we try to look at the efficiency of how we compute these masks, what we have here is a very compact representation that would be used in the implementation. And what we see is that when we process a query, we first compute initial masking offset that is not actually used, but it's something dependent on the nonce. And then we have this rule which tells us how to compute the next masking value from the previous one. And we see that if we want to increment the blue component and switch the red component, it actually requires just a few very basic operations like XORs and table lookups. Because these L values, you see, are dependent only on the key and can be pre-computed at the beginning of the session and kept in the tables. Or if need be, also computed on the fly if we have constrained resources. From the security point of view, this is what we require from our masks. And basically these two requirements tell us that we need the masks to be XOR universal. And if you look in the paper, there's some motivation, and we show that this is actually the case. The security analysis of pure OMD was done in 3 steps. In the first step, we look at the security of idealized pure OMD, where we use a true tweakable random function instead of a real-world primitive. And then in the next 2 steps, we bridge this idealized case with the real-world case, where we use an actual PRF. In the analysis of the idealized setting, we see that we have a very nice bound for privacy, and this is due to the fact that we use a true tweakable random function, and we arrange the tweaks such that every tweak in the encryption queries is different. This makes all the outputs of this function independent, so it's quite easy. And the analysis of authenticity is a bit more tricky. You have seen that there are many cases which can occur when we have some inputs to the compression functions. But if we do some lengthy and slightly involved case analysis, we can come up with this bound. Then, in the next two steps, we first replace the tweakable random function with the tweakable pseudo-random function. And then we construct the tweakable pseudo-random function with the modified XE construction proposed by Phil Rugaway, which uses these delta masking offsets and an ordinary pseudo-random function. And then when we put everything together, we get these bounds. We see that the bounds have a term which represents the security of the used PRF. And then we have contribution from the bounds from the idealized setting. And then we have these highlighted terms which come from using the modified XE construction. And this is maybe the place where there is room for further improvement because the using of the XE construction gives us two not very pleasant effects. The first is the birthday type term in our bound, which dominates the bound. And second is that we have to make sure that we compute and arrange all these masking values in a proper way. And this is a bit tricky. And if we mess this up in the implementation, let's say, this will lead maybe to broken security. It would be possible to avoid these issues if we had used a native tweakable compression function with both key and tweak input. And if we try to look for such, the most promising way is perhaps the tweaky framework proposed just recently. So maybe by modifying this approach from block ciphers to compression functions, we could have some nice native compression function which we could use. Because the whole point of trying to modify OMD to get pure OMD was to improve the efficiency of how we process the associated data. We also did some experiments. We implemented pure OMD, and then we compared the efficiency of pure OMD to the original OMD. On this figure, we have the cost of encryption in cycles per byte as a function of length of associated data for a fixed message length. And we see that both OMD and pure OMD improve as we increase the length of the associated data, but the improvement of pure OMD is much faster. And the difference in performances is getting bigger and bigger as we increase the size of associated data. And perhaps even more interesting is this figure, where we have the total cost of encryption in cycles. And we were looking at the encryption costs of queries which have message and associated data of the same length. And we see that this blue line, which comes from the measurements of the original OMD, and this red line, which comes from the measurements of from the pure OMD, are getting more and more apart from each other. And we also see the black line, which comes from the OMD, where we encrypt the message of the same size, but no associated data. And this nicely demonstrates that the processing of associated data is indeed almost free. And before I conclude, I would like to address the question of nonce misuse resistance. And I just have to say that the pure OMD is a purely nonce-based authenticated encryption scheme. And if the nonce is repeated, there is no security. All security is lost. In the pre-proceedings version, we had a claim where we said that besides having this nice efficiency as a small bonus, the authenticity is preserved to some extent if the nonce gets reused. But as Tomer Ashur and Bart Manning have shown, with a very simple attack, this claim is void. So this is not the case, and we will, of course, remove this small bonus claim from our paper for the proceedings version. And this is where I would conclude. So as you have seen, we have introduced a new variant of the OMD Caesar candidate, in which we are able to process the associated data almost freely compared to the original version. There is some room for the improvement if we can find a native tweakable compression function that would simplify the design. And also, the technique we have used can be quite easily adapted for sponge-based AE algorithms. So they could also benefit from having the AD processing almost for free. And in fact, from the point in time where we have submitted this paper, and now, there have already been some works presented, or there are some works which are waiting for publication that have actually shown that this is true. So that's everything from me. Thank you.
Thank you very much. Any questions? Yes.
So in your performance slide, this one, so there's only red star there.
Oh yeah, I think.
Please repeat the question.
Oh yes, so the question was that in this graph there is a single data point which doesn't lie on the curve, and well, to be honest, I'm not aware of any systematic reason that would imply this isolated data point, and I guess there was just some mistake in our measurements. I mean, with the point of these measurements was not to have some very precise results saying that this is the very precise speed of the algorithm. We just wanted to see if our intuition holds. So I think it would be possible to redo the measurements in a cleaner way, but yeah, I don't think that this means anything special.
Okay. More questions? So maybe I have one. Do you have a plan to modify the submission of OMD to the CISA competition, or?
Oh, this is not decided yet, but in any case, the original OMD remains our primary recommendation, and so far the only. So far there was no plan of trying to alter the algorithm to pure OMD or include some other variants we have shown in other places. So OMD still remains our primary candidate, as it has some other features that this pure OMD lacks, for instance, static associated data processing and parallelizability in the associated data processing. So no, the answer is no.
Other questions? Yes, please.
Maybe if you try to think about this, how to make some variant to have some defense against misuse nonce.
Oh, in fact, we do have a variant of OMD, which is supposed to protect from the nonce misuse. This was presented at ProofSec last year, and this variant is a two-pass scheme. So in our approach, we targeted the full nonce misuse resistance as defined by Rugaway in 2006. Where you have only very small degradation of security. So yes, we have that.
Okay, so let's thank the speaker again.